Right. Welcome everyone. Today I will present design of experiments DOE analysis conducted to reduce the excessive flush defect in an injection molding process. We'll go through the problem background, methodology of using both full and half factorial DOE, as well as discuss the key results, which factors and interactions are significant, and the recommended process settings to minimize flash. My name is Joe Urapa, and I have been working on optimizing this injection molding process. All right, first let's define the problem. Flash is the extra plastic that seeps out along the mold seams. It's a common defect that we want to eliminate during this molding process. Flush happens when molten plastic escapes the cavities, often due to too much injection force or speed or insufficient clamping pressure, among other reasons. In our case, we suspect certain process settings might be too aggressive and causing this flash. And the goal of this study is simply to use a structured experimental approach to find out which parameters are the culprits and how to set them to minimize or eliminate the flash. Right, to tackle this, we're using design experiments. DOE is a very powerful method that lets us vary several factors at once in a planned way and observe the effects on the outcome. This is more efficient and informative than changing one factor at a time, and it is also revealing uh, any interactions between factors. I decided on a full factorial design first with four factors at each two levels, that is 2 to the power of 4 design. And the output I measure in each run is the flash size in millimeters on the molded part. So this is the experimental setup. As you can see, we have set up the factors we studied at their low and high settings. A is the injection pressure, B is the pack and holding time, C is the injection fill speed, and D is the screw rotation speed in RPM. These ranges were chosen based on our engineering knowledge. For example, we suggest a higher inspection pressure or speed could force material out and cause flash. The pack time and screw speed could also influence how materials is packed and if excess materials is being delivered. The goal is to quantify how each of these factors influences flash. All right, first we run a full factorial experiment, which means every possible combination of these four factors at their two levels, that's 16 runs in total. I randomized the run in order to avoid any time-related biases, and the table as you see in the screen is a snippet on the representing the design metrics in coded form, where negative is low level and positive is high level for each factor. For example, run 1 was A low, B low, C low, and D low. For each run, we measure the results flash on the part. So the data range from as low as 0.22 millimeters of flash up to about 11.5 millimeter in the worst case. All right, so let's discuss the main effects. From the full factorial data, we have calculated the main effect of each factor. Basically, how much does flash change when we go from low level to the high level of that factor. So averaging overall, other factors. So here are the numbers. Pressure A had about 2.56 around what you call this millimeter effect, meaning high pressure caused roughly 2.56 millimeter more flash than low pressure on average. Speed C had a huge effect as well as to the plus 0.57 millimeters. All right, so that's high injection speed really increases flash a lot. Screw RPM or D was at 1.47 millimeters, a smaller effect but still positive. Pack time was effectively zero or negligible. Changing holding time from 1 seconds to 5 seconds did not change flash. All right. So initially it looks like injection speed is the biggest contributor, followed by pressure, then screw speed, and time doesn't matter at all. All right. Um, as the analysis of these factors' contributions, as I've said already, okay, we can look at the variation from each factors. Let's say, for instance, for injection speed accounted for roughly 80% of the explainable variation in flash among the main effects. And it's absolutely a dominant factor. Pressure was next at 15% and RPM is around 5%. This time was actually virtually 0%. So the implication is clear as per our analysis that if we want to reduce flash, we should focus on injection speed and pressure. Those are the heavy hitters. Scroll speed has a minor effect, and pack time can efficiently um, be set up to whatever is convenient because it doesn't affect flash at all. Okay, let's move on to the next slide. Yeah, so basically what we have here are the main effects and normal probability plot, which was generated using Python. And I have made also the graphs showing here which factors has high effect both in low and high. And we came to know that as discussed, the speed C is affecting much, followed by pressure, then the D. All right. So these are again the what you call the main effects plot with significant effects, plots. So using full factorial effects on probability plot, as you can see earlier, results for the full factor, you can say most of the smaller effects cluster along the straight line. These are likely just noise earlier, but a few points clearly lie off the line, specifically the main effects for pressure, speed, and RPM or D. So A, C, and D are far better than the line, confirming they are significant. Also, a couple of interaction effects stand out. The AC interaction and the CD interaction. So all other effects, including B and any other interaction involving B, hug the line, indicating they are not significant. So from this, we conclude factors A, C, and D and interactions A, C, and CD are statistically significant, while B is not. All right, so this matches our earlier effect ranking, plus it alerts us that interactions are actually present. So as you can see here in these interactions, the two important interactions, firstly, AC, pressure and speed, and CD, speed by RPM, are, I would say, the interactions that are very significant. This AC, pressure and speed interaction, was negative in sign, meaning the effect of pressure is big when speed is low, but when speed is high, changing pressure doesn't do much. So if we do plot flash versus pressure for two cases, one at low speed and one at high speed, we see a huge gap um, around this area. Okay, and CD This is also positive interaction. It means the positive of injection speed and flash is amplified when the screw RPM is high. All right, this is the table showing the reduced model effects, focusing on the factors that significantly have impacts or main effects, and then as well as the major interactions, and showing their sum of squares and their effects and their significance and the, the, the p values. Okay, so ANOVA result shows that all are statistically significant with p values less than 0.01, and and C, the interaction is like zero point zero 0.02 as well, which is still statistically significant. All right, moving on to the next slide. This is a regression model of the um, full factorial results. It's expressed as y bar flash is equals to 5.783 plus 1.278 for A plus 2.881 for C and 0.737 for D minus 1.317 for the combined interaction A and C plus 0.412 for the interaction C and D. All right, so based on this, we can have the settings as A to be 10 bar, C to be 12 millimeter per seconds, D at 200 RPM and B as 1 seconds. And these settings is could produce a minimal flash. Okay, this is basically the regression model. Moving into the next one, this is just to show the residual versus fitted values, as well as the normal probability plot for the full factorial. Moving to the next, we will discuss about the fractional factorial design and aliasing, as you can see on the screen. So these are the factorial design showing the 8 runs and generating some aliases as well, and using the residuals calculated later on using the formula. All right, so we're running out of time, so I'll just run through this presentation quickly and highlight few of these plots that is giving us a normal plot for main effects for half factorial, as well as the residuals versus fitted values and the normal probability of residuals. And for the regression equation for the full factorial and the residual comparison, this is as you can see in the equation, we're just removing those factors that are not having significant impact, like B and other interactions, which is not that significant. Okay, so moving on to the conclusions and recommendations. This is just quickly to say that the normal probability plot helps us identify significant factors by highlighting deviations from straight line, and we can say that time and RPM and pressure are significant. All right, sorry, the time is not significant, rather. Sorry for that. So this is the model development and validations that we can use regression for model equation, and model can predict the flash size using pressure, time, RPM with linear regression equation. And normal probability plot of residuals shows a linear pattern confirming residuals normal distribution. And yeah, the model validation confirms reliability for prediction, supporting its use in process optimization. So in terms of efficiency and limitations, we can say that factorial design reduces the runs to 8 using defining relations to be like D equals to ABC, improving efficiency. However, this aliasing causes confounding, between effects like A and B, C, D. So this limiting our distinguishing individual effects, and we can say that it has reduced runs, but yes, improve efficiency, but limits the identifying interactions, effects, and other parameters, which might be important later on. There is also a design trade-offs and recommendations that will take place between full and half factorial, because full factorial basically provide comprehensive insights into all effects and interactions without confining ideas to detailed analysis, while fractional factorial, on the other hand, offers fewer runs and increased efficiency, but as a result, it suffers from aliasing that can obscure true effects, and that's only useful for initial factor screening. So, as a design recommendation, a full factorial design is preferred for this case due to the accuracy and clarity and aligning with quality priorities. As a final insight and process guide, I would like to say that time uh, is not significant in this equation, but the important effect is this from the speed and pressure and other interactions. So this is very helpful presentation because it designs a focus to controlling pressure and speed to reduce defects efficiently. Thank you very much and have a good day.